In this video, we're going to learn how we can predict the direction of an induced current. And what I mean by that is if I take a magnet, in this case a bar magnet, and I move it towards a coil, I can see that the electrons move in a specific direction. In this case, they move downwards. If I move this magnet back away, I see that the electrons move upwards. If instead I flip around this battery if I flip around the magnet, and I move the magnet towards the coil, I see the electrons move upwards. And then if I remove the magnet, I see the opposite. I see the electrons moving downwards. So there must be some way that we can predict the direction of electrons based on how we're moving this magnet either towards or away from the coil. And there's a law, and this law is known as Lenz's law, and it will tell us how we can figure this out. The law states that the direction of the induced current in the wire by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field. Now that sounds really complicated at first, but essentially it says that the current that's induced is going to make its own magnetic field, and it's going to be in the opposite direction as the change of the magnetic field due to the motion of our magnet. Still sounds a little bit complicated, so let's see that as an example. If I bring this magnet towards the coil, then I am increasing the magnetic field in that coil. So when the magnet is far away from the coil, inside the coil, there's a very small magnetic field, but I'm increasing it as this gets closer. And I can see that by these little compasses in this animation, that the compasses are getting brighter inside the coil. Now, I also have to talk about the direction of a magnetic field. So in this case, I'm increasing it in a specific way. That is, here we have essentially close to zero magnetic field, but as I bring this closer, I would have a greater magnetic field, but I would draw that as an arrow. So if I drew field lines from that North Pole, that would be going from left to right, and so I've increased the magnetic field, but in a specific direction towards the right. Okay, so that's the first part. That is how the magnetic field has been changed in the coil. Now, Lenz's law states that the current that's induced will be such that it's going to oppose this change. It's going to make a magnetic field in the opposite direction. So let's look at the current again. If I bring this towards, I see that the electrons are moving downwards. And that's only when it's actually changing, of course. As soon as I stop, they stop moving. So if we have electrons moving downwards, that means that we have a current that is moving upwards, because of course conventional current is the flow of positive charge. So here we have then current that's moving upwards, and if we use our right-hand rule for a solenoid, then as we wrap our fingers upwards around this coil, we see that it would make a magnetic field towards the left. And so there we have Lenz's law. As this creates a magnetic field towards the right, then we have the electrons moving in such a way as they are making a magnetic field towards the left. As another example, we can see what happens when I move this magnet away from the coil. Now, as I move the magnet away from the coil, I'm decreasing the magnetic field there. So I had a magnetic field due to the bar magnet towards the right, and I've decreased that. And when I do that, let's see that again, I see that the electrons move upwards. If the electrons are moving upwards, that means I have a conventional current moving downwards. If I use my right-hand rule, then I see that the electrons are moving in such a way as to make a magnetic field towards the right. So I have decreased the magnetic field as I remove the bar magnet, but then the electrons are resisting that change, and so they are making a magnetic field in the opposite direction of that change. So one way I like to think about Lenz's law is that electrons just don't like changing magnetic fields. They would like everything to stay the same, and so when you try to change a magnetic field, they will act in such a way as to prevent that change. And there we have it. That is how you predict the direction of the current in a coil due to a changing magnetic field.